Hi, welcome to another complex numbers video, our last video dealing with polar form. We're simply going to go through two examples in this video, some complicated examples, and you may need to pause the video as we go because I'm going to go quite quickly. Example 1, find all possible values of k given that the modulus of 2 minus 3ki is equal to 8. Remember those straight brackets means modulus, and the modulus is the distance away from the origin, and we use Pythagoras. So let's go r squared is equal to 2 squared, which is the real bit squared, plus the imaginary bit squared, minus 3k all squared. 2 squared is 4, minus 3k times minus 3k is 9k squared. And we square root it to get the modulus. Now we were told the modulus is 8, so let's put the statement equal to 8. Let's now square both sides, subtract 4 off both sides, and then we're going to divide everything by 9 to get k squared is equal to 60 over 9, and k we can square root 60 over 9 to get k. Now remember, when we square root numbers, we end up with two solutions. So the first solution is 2.582, and our second solution is minus 2.582, which I've rounded both to 4 significant figures. There's two possible values of k which make this statement correct. All right, example 2 is a real tricky one. If the modulus of z is equal to 1 and z is not equal to 1, prove that 1 plus z divided by 1 minus z is purely imaginary. Now we know z is just a complex number. I just want to quickly point out why they say z is not equal to 1, because on the bottom here, if z was 1, we'd have 1 minus 1, which is 0, and it wouldn't work because we can't divide 0. So that's why they tell us that. Okay, so since z is equal to the complex number a plus bi, we're going to replace the top with 1 plus a plus bi. We're not going to use a plus or minus, we'll just use a plus. And on the bottom, we're going to replace it with 1 minus z, which is a plus bi. Tidy up the bottom and make it 1 minus a minus bi. And then we're going to take this fraction and multiply by the conjugate complex number. Now, this is a bit tricky, but the conjugate, remember, we take the imaginary bit of the denominator and we swap it from a minus to a plus, but we must multiply by the same on the top and the bottom, because that way we're multiplying it all by 1. Okay, now this next bit, welcome to pause it and check it, but I'm multiplying the top all out. I just pretend there's brackets around both of them and multiplying everything out, and I'm going to do the same on the bottom. Now, this part here, remember I squared is equal to negative 1, so we're going to multiply the top b squared by negative 1, and on the bottom that minus b squared also gets multiplied by negative 1. Now we're just going to do some simplifying, so we're looking around for like and unlike terms and simplifying the top and simplifying the bottom. Right, now the last little trick I'm going to do here is I'm going to factor out a minus 1 from the top bit here so that we end up with minus bracket a squared plus b squared. Okay, let's come back to the idea that the modulus, we were told the modulus of this z is equal to 1. The modulus is found by working out the square root of the real bit a squared plus the imaginary bit b squared. So since we were told the modulus was equal to 1, we're going to put this equal to 1, and then if I square both sides, I get 1, because 1 squared is still 1. 1 is equal to a squared plus b squared. Now what we can do with this little part is we can go back here and substitute a squared plus b squared for 1. So we can replace both of those with 1. On the top, when we simplify it, we're going to get 1 minus 1, which just leaves 2bi, and on the bottom we're left with 2 minus 2a. Now if I take that little expression and just put the I out the end, I'm allowed to do that with fractions, you will hopefully see that I've now got no real parts and an imaginary part, which is made up of 2b divided by 2 minus 2a. So I've proven that this is purely imaginary because there's no real parts to it. It's just an imaginary component. Right, that was a lot. Thanks for watching.